Hello, it is both an honor and a pleasure to present my scientific paper entitled Design of a Novel Analog MPPT Integrated Chip Used in a PV Systems Applications into this Congress. Beginning with the outlines of this presentation. The presentation is organized in the following way. Section 1 presents the introduction. Section 2 discuss about proposed system architecture and chip layout. Section 3 discuss the simulation results. Section 4 discuss the design of the analog MPPT control circuit. Finally, conclusions and perspective are made in Section 5. Due to the growing demand on electricity, the limited stock and rising prices of conventional sources, such as coal and petroleum, etc., new energy and clean fuel technologies are being intensively pursued and investigated. Most of the renewable energy from solar, hydropower, biomass, geothermal, and wind are converted into electrical energy to be delivered either to the utility grid directly or isolated loads. Solar energy has become a promising alternative source due to its advantages, environment-friendly, and has less operational and maintenance costs. We move now on to proposed system architecture and chip layout. The synoptic diagram of the whole photovoltaic technique is presented in the following figure. This controller directly uses the voltage and current of photovoltaic array to look for the equivalent operating maximum power point. A shunt resistor, RSH, operates as a current sensor of the PV array output current. A voltage divider composed of two resistors, R1 and R2, is to determine the PV generated supply voltage. DC-DC boost power converter. In our case, the output voltage is higher than the one delivered by the PV panel. Loud, in our case a simple impedance, analog MPPT controller, allow the track of the maximal power point of the PV array, which depends on climate conditions. A novel analog MPPT technique suitable for PV system applications is presented and validated by simulations using the circuit-oriented simulator approach as ISIS. The proposed analog technique is based on the generation of a reference power signal, PREF, to be followed by the PV panel's real power, PREAL, since this PREAL is lower than the maximum power generated by the PV panels. This figure shows the simulated different waveforms corresponding to the above-mentioned power at different irradiation levels. The integration and miniaturization of ASIC-specific integrated circuits play an important role in improving the performance and reducing the cost of electrical systems. Once the circuit specifications are filled in the simulation, the circuit diagram is created using the virtual schematic editor. The resulting layout has to check certain technology-dependent geometric rules, design rules. Once the circuit has been designed, we can move on to the manufacturing stage. This figure illustrates the steps from schematic to fabrication. The synoptic diagram of the photovoltaic technique is depicted in the following figure. Cadence is an electronic design automation, EDA, environment that allows integrating in a single framework different applications and tools, both proprietary and from other vendors, allowing to support all the stages of IC design and verification from a single environment. Figure shows the internal block of the designed analog MPPT controller IC. We move now on to simulation results. The two-stage seamless operational amplifier includes four major circuitries: a bias circuit, an input differential amplifier, a second gain stage, and a compensation circuit. The bias circuit is provided to establish the proper operating point for each transistor in its saturation region. The input differential amplifier block forms the input of the op-amp and provides a good portion of the overall gain to improve noise and offset performance. The second gain circuit block is typically configured as a simple common source stage so as to allow maximum output swings. The purpose of the compensation circuit is to maintain stability when negative feedback is applied to the op-amp. This figure shows the designed AOP topology and its symbol, and this figure presents the simulated gaining phase of the designed AOP. The simulation result shows voltage gain of 95.56 dB and phase margin of 49.5 degrees. The current sensor of our circuit will consist of the current sense resistor and the differential operational amplifier. The current sense resistor will be connected to the solar panel negative board. The simulation of the current sensor is obtained by using DC frequency sweep analysis. An example of simulation results are shown in the following figure. The simulation of the voltage sensor is obtained by using DC frequency sweep analysis. The simulation of the voltage sensor is obtained by using DC frequency sweep analysis. An example of simulation results are shown in this figure. The analog multiplier is used to compute the instantaneous output power of the PV array. The design multiplier architecture is presented in this figure. The following figure presents a transient simulation example of the multiplier simulation. The schematic circuit and its symbol of the Schmidt trigger, hysteresis, is shown in this figure. The following figure shows the transfer function of hysteresis 1 and hysteresis 2 blocks. The bandwidth 1 of the hysteresis 1 block, well defined by epsilon 1 and epsilon 2. Is set by the user and is based on current ripple and modulation frequency considerations. The bandwidth 2 of the hysteresis 2 block, well defined by epsilon 3 and epsilon 4, must be greater than bandwidth 1. The pref generator, shown in this figure, is used to generate reference power signal. The resistors RB and RPT serve to tune the stable output pulses. The following figure presents transient simulation of the pref generator circuit. Sample and hold (SH) circuits are critical in converting analog signals to digital signals. The design sample and hold circuit is presented in this figure. The following figure presents simulation results of the design SH circuit. For the design of the proposed new technique, an implementation of the different blocks under the cadence environment has been developed. We move now on to design of the analog MPPT control circuit. This IC is used in the implementation of analog MPPT controller in order to attain stable maximum power point of the solar array in a short time duration. The circuit layout is depicted in this figure. Below are some of the most important layout rules of CMOS transistor matching. Locate the transistors in the same direction and as near as possible. Both the parallel transistors and the near transistors assist in reducing transconductance variations. Use the same fingers for all the matched transistors. Use of dummy gates to reduce the effects of engraving. Use common center design techniques. The matched transistors should also be separated into an even number of fingers and arranged symmetrically. Once circuit specifications are fulfilled in simulation, the circuit layout is created using the Virtuoso Layout Editor. We close this presentation with conclusions and perspectives. During this work, we have ensured the proposed MPPT control strategy has the ability of fast tracking of the MPP for PV systems. The proposed analog MPPT technique gives a maximum efficiency of about 99.4% at 1000 watts per square meter with an optimum number of electronic functions. The integration and miniaturization of application-specific integrated circuits, ASICs, play an important role in performance improvement and cost reduction of electronic systems. Our future work aims to develop the new analog technology on a grid-connected PV system, integrate the new technique to an LVDC conversion chain. Further analysis is required, in particular schematic and parasitic extraction. A second cycle of the circuit will be necessary in the future in order to solve the problems that occurred after the first realization of the integrated circuit. Thank you for your attention.